Hello, everybody. I'm Omar, and I'm with Gehed, Munir, Shahat, Yahya, and Saif, and we're going to be talking about optimizing LLMs for speech interactions under the supervision of Dr. Nouri Saqra and Dr. Ahmad Tawfiq from Microsoft. So first, we're going to talk about our objectives and motivation. Then we'll talk about how we went about it, and then we'll give you a demo, talk about how we obtained testing and results, and finally, we'll talk about our empowerment outcome. AI, LLMs, ChatGPT, it's as if every time we open the news, there's new information about artificial intelligence, and for good reason. We went from GPT-2, in which we would take 25 tries just to get some good human-like output, to GPT-3, where we are able to get personalized responses and even play games with it, to GPT-4, where we can now give it speech input and it outputs speech back. And how would we go about this? Well, first, you would take an input speech and pass it to an automatic speech recognizer, and this would output text. This text is given to a large language model to perform processing and give a response. This response is then passed to a text-to-speech model, and this is where the speech is. Well, all of this looks good, so where do we fit in? Well, imagine there was a problem in any one of these stages. Well, then any large language model or any speech-to-speech model will suffer these problems. So what we did is we looked at every one of these stages and tried to find problems that exist in all of these models and try to fix these problems. Because we wanted these problems to exist in a lot of different models, we decided to make sure that these problems were not domain-specific and that our solutions to these problems would be easy to implement and accessible. After this, we created a prototype for this model. We called it Speech Llama, or Salama for short. And now, Shahat can come and talk about the first problem.
All right. Okay, so starting with the first problem that we targeted, which is that LLM's responses are usually very long, formal, and are not interactive. So here's an example of Llama 3. We can play it.
With your career at times. Here are some steps you can take to help you figure out what you want to do. Reflect on what you value in a job. Consider what motivates you, what you enjoy doing.
That guy over there already got bored. And this is actually the problem that we're trying to target here. So we tried two different solutions. The first solution we tried was prompting. We actually tried 3 types of prompting: few shots, 0 shot, and role playing on 3 different LLMs: Llama, Gemma, and Mistral. The second solution we tried was, fine-tuning. So we simply trained the 3 LLMs on 2 different data sets. Both of them were simply subtitles from movies, aiming to make the model's responses more suitable for speech and interaction. And now for the results, we evaluated them using uni-eval method, which is simply choosing an LLM to be a judge. And we found out that by combining a few shots of prompting and Llama 3.1, we've got the best model. And here is a response of Llama 3.1 after applying prompting. And as you can see, the response now is shorter, less formal, and more interactive. It even ended up with an open-ended question, and that's it. And now Saif will continue with the second problem.
So as Omar discussed in the first system architecture, our first stage is the automatic speech recognition. So in this stage, we use the state-of-the-art model, which is OpenAI's Whisper model. And in this, we find one problem where it still makes mistakes in recognizing rare and personal names. So here are 2 examples that illustrate this.
Thierry.
So in the first example, the name was supposed to be Thierry, but it actually outputs theory. And in the next example, we can hear it.
Abigail.
So the ground truth was actually Abigail, but it outputs Happygale. And these inaccuracies can lead to significant misunderstandings when ASR is used in critical systems such as customer service. So our solution for this is to increase the training data for rare names. And one technique to do this is data augmentation. So we design a simple workflow. We first start by web scraping 20,000 names. And these are real spoken names from people around the world, from websites like forvo.com and howtopronounce.com. And then we use the sentences from the LibriSpeech dataset, which is a large speech dataset. And then we augment these sentences with the names that we web scraped. And we analyze 3 techniques for name replacement. The first technique we call vanilla replacement. The next technique we call pitch and audio matching replacement. And the third technique is RVC replacement. So a deeper dive into our methodology. We start by extracting the sentences from LibriSpeech where it contains a name. And we do this by searching by a common names list through the dataset. And then we use whisper timestamp to obtain exactly where the name was uttered in the sentence. And now we have all the information we need to start audio processing. So we start with audio processing the sentence. We first start by time stretching the region where the name was uttered in the sentence to make it exactly match the length of the name we are going to replace with. And then we write pad the sentence to make it 30 seconds long. Moving to the processing for the web scrape names, we first start by removing the silences in the beginning and the end of the audio clip. And then we right and left pad to make it exactly aligned with the original name in the sentence we are going to replace. And then we make it also 30 seconds long in order to maintain a constant shape for all the inputs. And now we can replace the name. And in doing so, we create different versions of the sentence, each with a different name. But actually, we encounter a problem. And this problem, you can actually tell that there, in the MEL spectrogram, there's a diversion where we replace the name. And now Omar will explain how we overcame this diversion.
Okay, so the first method we used to try to solve this problem was pitch and volume matching. So to perform the pitch and volume matching, the first thing we focus on is pitch matching. We take the original audio and we try to match it to the replacement audio. So to do this, we would subtract them. And to do that, we would just use Labrosa's pitch matching function. So that part was easy. The harder part was the volume matching. So in order to do this, we would actually calculate the root mean square, or the RMS, which gives us the average power between the two volumes. And after this, we would get the ratio between the RMS, and now we could actually map the original audio to the replacement audio. The second method we tried to use was RVC, or retrieval-based voice conversion. And first, let me actually give you an example of how this might sound.
Hey guys, it's SpongeBob here, and I'm gonna help Omar, Yahya, Gad, Shah, Munir, and Sif explain retrieval-based voice conversion.
Okay, I'm not sure if you guys heard that, but I think we all know that SpongeBob never said Shah to Omar, Munir, Sif, or Yahya, but somehow it was able to pronounce this well. So how did we do this? We would actually just use an RVC, retrieval-based voice conversion model, to perform this. So how did we utilize this? We trained it on 240 speakers from LibriSpeech for 50 different epochs. And after this, we now have a good RVC model that is mapped to this LibriSpeech speaker. And now we can make the LibriSpeech speaker actually take this pronounced word that we got from howtopronounce.com or from any web scraped website, and we can make this LibriSpeech speaker now say it. And we would generate this new audio file, and it's as if the speaker is saying the entire sentence by himself. And if there was a if there was a male to female conversion or a female to male conversion, it would sometimes not sound that great. So to fix this, we found that a good pitch shift was 12. And we can now listen to the example of what this might sound like. So you can see that it actually sounds different, and this is actually the RVC model now pronouncing the name. So now if we look at the new improved mouse spectrogram, we can see that the vanilla replacement has the highest divergence. The pitch shifted has a slightly lower divergence, and the RVC replacement has the lowest, and this is because it's as if, again, it's pronouncing the entire sentence by itself. So it sounds good, but how will this fare in terms of the word error rate? Chet will go ahead and talk about that.
Okay, so now moving to the results. How did we evaluate our results? We used two different metrics. The first metric we used was word error rate, and the second metric was named entry recognition, focuses on how the model can accurately identify persons' names. And we've done two different separate testings. The first test we've done was on the Whisper by testing it on the 3 augmented dataset without any fine tuning. And as you can see, it showed a really high word error rate and low named entry recognition, comparing it to testing it on just a lip speech. And this shows that the model has a difficulty in identifying rare names. The second test we've done was after fine-tuning Whisper on the 3 augmented datasets, and actually showed a significant improvement for all of the methods. However, vanilla replacement was actually the best. It showed a significant improvement in the WER, as it decreased dramatically from 17.54 to 3.31. And it also showed improvements in the NER. For instance, the recall increased by almost 5.6%. And here's an example of the 3 methods. And as you can see, the vanilla replacement identifies the name Apotheca almost correctly. However, the 2 other methods identified it as about. And now Munir will continue with the third problem.
Thank you, Shad, for showing the solution. I'm moving on to the third problem that we tackled in the thesis project, which is regarding the ASR. So usually what the ASR does is it takes an input audio file, and then it generates multiple sentences that the ASR claims one of them should match the input file, the input audio file. And then it gives each and every sentence of those a probability of how close this sentence is to the input audio file. Then it orders them and picks the highest of them to represent the audio file. But what's the problem with this approach? First of all, it's not guaranteed that the top probable hypothesis is the one that best matches the input file. Second of all, there isn't a guarantee for any grammatical mistakes, and there isn't a built-in way to provide a solution for those problems. This is a real-life example from our dataset from Hyperdice. As we can see, those are the 5 generated sentences, 5 generated hypotheses. And usually the ASR picks the best probable hypothesis. However, the ground truth, as we can see, best matches the third hypothesis. So the problem here is, how could we know which of those generated hypotheses best describes the input audio file? Yahya will explain the solution.
So how do we tackle this problem? We decided to use large language models for post-ASR correction. As you can see here from this architecture, our 5 input hypotheses are passed as an input to 3 LLMs, Llama, Mistral, and Gemma. And we decided to use these specific LLMs because they are open source and they have state-of-the-art results. And the role of each LLM is to generate a sentence that should be grammatically correct and should be the correct transcription according to its natural language understanding. Not only that, after generating the sentence, we also map this generated output to the shortest mapped hypothesis. We see the closest hypothesis to this generated output, and we choose it as the shortest mapped hypothesis. So in total, for each LM, we have 2 outputs, 1 generated and 1 shortest mapped hypothesis. And so total, we have 6 outputs. They are all passed as an input to an LLM judge. So the role of this judge is to choose only one of these inputs to be the final ASR transcription output. And we decided to use Mistral as the judge because of its great experimentation results, as Munir will elaborate on in a few minutes. So how do we test and evaluate our approach or methodology? First, we gathered our data sets. We used high-paradigm data sets, which consists of 8 different data sets, which are different in terms of subjects, contexts, accents, and several other aspects. And then we decided to group these data sets according to their complexity, because I cannot say that I got a good word error rate in a certain data set, but a bad one in another data set, so I need to have a fair comparison. So this is before the grouping. We have the 8 data sets, and this how they are grouped into low complexity, medium complexity, and high complexity. But how did we actually do this? So basically, as the ground truth is more different from the input hypotheses, the more complex this example or this data set is. And the more grammatical errors the ground truth has, the more complex it is. And the more accents that the data set has makes it a more complex data set. So let's see these 3 examples. As you can see from the top left example, the ground truth is very close or very similar to the input hypotheses. So this makes it a very easy example for the LLM to deal with. Moving into a more difficult example, the one in the middle, the word then is repeated in every input hypothesis, yet it is not present in the ground truth. So it makes it a slightly more difficult task for the LLM to deal with, yet it is still feasible. And now moving into our final example, you can see the ground truth has errors and mistakes. Like the word end is repeated, and there is IWI, which is not even present in the input hypotheses. So that makes it a very difficult example for the LLM to deal with, and it puts it in one of the most complex data sets. Our final step to start testing and evaluation was choosing our baselines for testing. So we chose 2 baselines. The first one is choosing the first hypothesis as the final ASR output. As Munir elaborated earlier, the ASR systems typically use the first hypothesis to be the final transcription. So we decided to use this as one of our baselines. And the second baseline is using the shortest mapped hypothesis to the LLM output as the final ASR transcription, and we got this from our literature survey. And now Munir will guide you through our numerical results.
Thank you, Yahya, for clarifying the solution. So this is a table of the results for our approach. As you can see in the leftmost of the table, we can see our data sets arranged from the lowest complex to the highest complex at the bottom of the table. And at the rightmost of the table, we can see the difference in the improvement percentage for each of the data sets. So in the middle of the table, we have each and every LLM that we used and its performance. The less the number is, the better the performance. What are the findings that we can get from this table? First of all, is as you can see, the approach is really working with low complex data sets, somehow with medium and moderate complex data sets. But when the complexity increases, it's very hard for our approach to perform. Second of all, working with different LLMs in the middle of the table gives us diverse outputs and guarantee better performance and less grammatical mistakes. And final of all of the findings from the table is a judge that we used right before the difference column, which guarantees better performance than each and every individual LLM that we used. And now let's move to the fun time with Gihad and the demo.
Okay, thank you, Munir. So now with the fun part, we will show you a small demo where we combined all our progress for the 3 problems. And in the demo video, please note the small details as we will comment on afterwards. Hi, I want to send a thank you note for my amazing thesis supervisors, Dr. Nouri Sak, Dr. Ahmed Tawfiq. And I also want to thank the amazing committee, Dr. Amr Al-Mugi, Dr. Mikhail, and Dr. Saif Al-Dawlatli.
That's so awesome. So, you want to write a heartfelt thank you know to your supervisors and committee members. Let's get started. Who would you like to start with? Your supervisors or the committee members?
Okay, so Okay, as you have seen in the demo, we are showing the full pipeline of our work. So beginning with the first stage, the ASR stage, our work with the ASR stage was presented in problem 2, where we focused more on recognizing names, and we can see here that the ASR was successfully recognizing most of the names in the given input. After this, from the ASR, we get the output text, and we get 5 different hypotheses, where we take those hypotheses and we input them to the post-ASR stage, the stage that was discussed in problem 3. Then we get a final text, which is the full transcription, which is this one presented here. This is after the post-ASR correction. If you noticed in the in the recording, there were some stuttering, so there were some noise in the audio, and this was also handled correctly. Then the third stage, we take this text, we input it into an LLM model as described in problem 1. This model was Llama 3.1 with few shots prompting, and we get a new response that is suitable for a speech setting, short, and good enough for our purposes. Then after this stage, we take this text output, we input it for TTS, the fourth stage. Our TTS used here was the parler TTS, which is to speak in French. This TTS took this text response and converted to an audio, the one you listened to in the video. After this, we conducted some testing over the full pipeline using this demo. We had the testing with students from our department and other students and our friends. We had the demo with 40 people, and we presented to them a survey that they filled, and about 88% of the students, they reported that they got very to mostly accurate transcriptions for their speech, and also like about 75% reported that they got all or most answers to be super accurate. Now, after this, we will be presenting the part related to the empowerment outcome, the outcome that we got after all this work for about 12 months. So for our empowerment outcome, our outcome is submitting 2 research papers tackling each of problem 2 and problem 3. The first paper is about speech data augmentation with ASR on rare names, as you can see in here. And the second paper is about post-ASR correction using large language models. And since like both papers are mostly in some sort of a separate areas, that's why we splitted them into 2 papers. And we have come to the end of our presentation. Thank you all for attending, and thank you for our committee.